Hello. In this video, we'll give you the guide through all the questions in the Handout 9. So Handout 9 is about the magnetic induction and the Faraday's law. So we'll begin with the definition of the magnetic flux. Okay. So for the magnetic flux, if we consider a surface or an area A here, with a magnetic field across the area, passing through the area, okay? You can define the magnetic flux as the dot product between the magnetic field B and another vector A that is proportional to the area, okay? So that will give you the total number of the field lines within the area, okay? So let's consider example 1. They talk about a solenoid. Okay. So we got a solenoid with a length 8 centimeters. So I just say that the 8 centimeter length is L, and 1.4 centimeter in diameter. So I will say that the diameter of this solenoid is D, okay, and there should be a wire over here, and with given current, we should come up with the magnetic field across the solenoid, through the solenoid, okay. And then they also give you the current through a solenoid of 68 milliamp. And here the solenoid has 340 turns. And the question is, what is the magnetic flux through 1 turn of the solenoid? So if I just pick 1 turn of the coil and just only one area, with the area A, which is equal to pi d square over 4, while d is a diameter. So what will be the magnetic flux through the 1 turn of solenoid? Okay, so in this case, we can see that the area and the vector A is parallel to the magnetic field. So when A is parallel to B, when vector A is parallel to vector B, so we're gonna have the dot product between A and B as simply AB. Yeah. So here, the magnetic flux, would be just AB, while A is the area and B is the magnetic field. So how do we find the area? Okay, so the area is pi d square over 4, where d is the diameter that given from the question. And what about the magnetic field? So the magnetic field in the solenoid is for you to use the Ampere's law. The Ampere's law for the solenoid, in which you start with integrate B dl equals to mu times I enclosed. So the integration on the left hand side will give you BL. On the right hand side, the total current enclosed by the Ampere's loop is the N, or the number of turns, times by the current in the solenoid. Okay. So our magnetic field B would be the mu 0 Ni over L. Okay. So here is the expression of the magnetic flux. Okay. So if you substitute all the parameters in the SI unit, you should get the magnetic flux in the unit of Weber. Or the Weber is actually Tesla times square meter. Okay, and we come to another definition, Faraday's law. So let's see here. The Faraday law states that the induced EMF is stand for the electromotive force. In the unit of voltage. In the unit of volt, or we can say that the EMF is actually the voltage or the potential difference that is created by something. So in this case, the induced EMF in a closed loop is equal to the negative of the rate of change of the magnetic flux. Okay? So we can see that start from the magnetic flux. If the magnetic flux got changed, we tend to have the EMF, or we tend to have the voltage, or the change in the magnetic flux tends to create a potential difference within the circuit. Okay? And the magnitude of the EMF is actually equals to the rate of change in the magnetic flux. All right? So let's see the example 3. They say in a physics laboratory, the coil with 200 turns N enclosing an area of 12 centimeters square. Okay, rotated from a position where its plane is perpendicular to the Earth magnetic field. So here what do we need is the Earth magnetic field. All right, Earth magnetic field. So we start from being perpendicular. So this is the coil. So okay, so I'll draw it better. So this is the coil, and with N turns and with the area A, and then after that, after we rotate this coil a little bit, the plane becomes parallel to the field. Okay. So in this case, the first case, so when the plane is perpendicular to the field, so you can see that the magnetic flux is not zero. So because there is some magnetic field lines coming through the plane. But if you see the second case, that the plane become parallel to the magnetic field, so here you can say that the flux is zero because there is no field lines passing. Okay, so they ask you to find the average EMF induced. Okay, so firstly, we say that the EMF is d phi by dt. But if we talk about the average EMF, the d phi by dt, this will become the delta phi over delta t. Okay, so the delta phi over here is just going to be, in the first case, the magnetic field times the area and times number of turns. Okay. And then divided by the time given. Okay. And this will be your answer. Okay. So the reason that we need to time the number of turns into this equation because of for the magnetic flux. If you have just only one loop of the coil, the magnetic flux or the magnetic field lines will go through just only one area. Okay. But if you have more turns of the coil, so the flux will go through another area. And if you have the n turns, okay, so the area will just become NA, right? So this is the reason that we add up the number of turns into the equation. Okay, so example 4. So in the example 4, we will consider the case of varying magnetic field. Okay? So here it's just simple. I'll just say that this constant is C and this constant is D, and the function of the magnetic field is Ct plus dt to the 4. And then the magnetic flux as a function of time, it will be just pi r square, or as they say that the coil has the radius of r, so it's a pi r square, and times by Ct plus dt to the 4. And the induced EMF will be simply differentiate the function phi respect to time, and what you get is C plus 4 dt to the cube. And then whenever you want to consider the current, okay, you can simply use the Ohm's law, because we consider the EMF as voltage. So when you consider Ohm's law, you just get E equals IR, and the current is EMF over R. When R is when R is the resistance, not the radius. Okay. So you should come up with something like pi r square over resistance and times by those functions at the back, and that will be your answer. Okay, and then for the number 5, a square loop. Okay, so they gave you the size of the square loop, which I will just call it. I will call it the L, or the length. I will call this the width, or W. So this is W, this is L. So each move at a constant speed V into a region of transferred uniform magnetic field B. Yeah. So if you want to calculate the magnetic flux on the first case, so we're just gonna consider this region A. Okay. So if I define the distance x as the distance traveled by the loop, yeah. Here, the area that the magnetic field is passing through will become W times x. Okay. and the magnetic flux. Yeah. So this will be the magnetic field times the area, or the magnetic field times Wx. Okay. And the EMF, it will be d phi by dt, and B and W are the constant, so what left for the differentiation is x. And then what you get for the A is you get the EMF of the minus B W V, where V is the velocity. Okay. So then if one wants to calculate the direction for the induced EMF, okay, here is what we are doing. Okay. So we will say that the direction for the increasing flux is going inside, going into the paper, increasing flux. So if you use the right hand rule, so if you use the right hand and you put your thumb into your paper, you find that your right hand will make a clockwise circle. But for the EMF, it will be opposite to the right hand. So in this case, for A, we can find that the direction of the EMF is counterclockwise, or we can say that, okay, the current is flowing in this direction, counterclockwise. Okay. Okay, so for the B, when the loop is completely inside the region, okay, so when it is completely inside the region, so here I'm drawing the region of the magnetic field, okay, like this. Then when your loop is completely inside, okay, and you have the loop of the size L times W, so, and with the magnetic field B, so the magnetic flux will be BWL, which is a constant. So when you have constant, you find the induced EMF by d phi by dt. So you differentiate the constant, you get 0. Okay? So in part B, the answer you get is 0. And in part C, when the loop is leaving the region, yeah. So what is happening when the loop is leaving the region? Okay. So it is traveling to the left. Here it's leaving the region. And here is the distance x that it is leaving the region. Okay. So we consider this area A where the magnetic field is passing through. And for this length, it is defined as the L minus x. Okay. So when x is increasing, or when the loop is traveling, the area keep decreasing. So the area is now is going to be W, or the width of the rectangle, times by the L minus x. So the magnetic flux will be B times the area, or times the W, and times L minus x. And the epsilon, or d phi by dt, using the same method, yeah, you should easily get the answer B, W, and V. Yeah, and then when you consider the decreasing flux, yeah, so your magnetic field is coming into the paper, going into the paper. So decreasing flux will cause you the change that is coming outside. Okay, so when you cause the change that coming outside, use the right hand rule. You're gonna get the direction of. Sorry, you can. When you use the right hand rule, you're gonna get a circle with the counterclockwise circulation. But with the induced EMF, it is opposing the right hand rule. The direction that you get is becoming clockwise. Okay, so you can say that the EMF in part C, it is flowing in the clockwise direction. Okay, so this is an example of Faraday's law when you vary the area. Okay, so firstly you come up with the examples that you try to vary the B. Now you do the example that you vary the A, and yet another example, we come up with the example that you vary the angle. Okay, because you have the flux that is defined by B dot A, which is AB cosine theta. So whenever this theta is changing, for example, if you get a coil here, and the coil is within a magnetic field, and the coil is rotating. So when the coil is rotating, that means the angle theta here is changing. Okay, so that's the idea behind this. Okay, so then when I look at this as a side view again, so I turn the system around. So I have the magnetic field in this direction, and then here is my coil, yeah, with the area A, and then the angle that the coil is making with the magnetic field is, I call this the theta equals omega t. Okay, and then here is my vector A. Okay, so the dot product between the B and A over here, it will give you the expression of A B sine omega t. Okay, so so this is where we can define the magnetic flux as a function of time. So when you define the magnetic flux as a function of time, you can easily find the induced EMF. So you can just differentiate this one. And then here's what you're gonna get. You're gonna get the EMF as a function of time, as the cosine function. Okay. So example 7. So this example is about the motional EMF. Okay, so you consider a conducting rod with the length L. Yeah. And it is placed in a uniform magnetic field B. Okay, so I draw some magnetic field here. And it is moving with a constant speed v. Here is a constant speed. Okay. And then the ends of the rod are connected to a lamp. So give you the lamp here. Here's the lamp. Okay. So here, so when this wire is moving, yeah, what happened is the area over here, the area on this circuit is increasing. Okay, so the area, when the area is increasing, what happens? Yeah, so it will, so presumably the magnetic flux is also increasing. Okay, so here we can sketch the area as a function of time, as the product between the distance x and the length L, and the magnetic flux will be the magnetic field times the area A. So that will become the BXL. And then the induced EMF it would be the BL as a constant times by the dx by dt, in which the dx by dt is actually the velocity v. So here you can get the magnitude of the EMF as BLV. Okay, and the induced current from Ohm's law as BLV over R. Yeah. Okay. So what about the direction of the induced EMF? Again, we have increasing flux because the increasing area. So now the change in the flux with the right hand rule, it is in the clockwise direction, but the EMF with the minus sign here, the EMF in contrast, it is in the counterclockwise direction. So that means that we have the EMF here in the counterclockwise direction. And we can calculate the induced EMF, we can calculate the induced current as well. Okay, so for number 8, it is continue from the last example. Okay, so when you pull out the bar here within the magnetic field, and you get the induced EMF in the counterclockwise direction. if you consider just only the green bar here, you have the current I flowing within the bar. And when the current I flowing within the bar, okay, so the displacement of the current, or the vector L, is going upward. So, and when the magnetic field is going into the paper, using the right-hand rule, L cross B will give you the Lorentz force, or FB, going to the left-hand side. Okay, so in order to fight or to compete with the FB to the left direction, you need to do some external force F to pull the bar to the right direction. Okay, so when external force equals to FB, yeah, this the motion of the wire is in equilibrium. Okay, so the equilibrium here, it means the constant speed. So this is a constant speed that your question is mentioning. Okay, so the key stuff is we need to calculate the Lorentz force from there. Okay, so for the part A, the equation asks you to show that the force needed to move the bar at the constant speed is given by this equation. So we can kind of combine the definition of Lorentz force, FILB, with the current that is induced. Yeah, so it is the same induced current that you find from the last question. So it is BLV over R. Okay, so this will become just BLV over R times the LB, and this will become B square L square V over R. So that's the answer for the part A. And for the part B, show that the rate of work done, here we mean it is the meaning of the power. So show that is equal to the power loss in the resistor. Okay. Okay, so on one side, we calculate the rate of the work done. Okay. So we can use the definition of the power as the differentiation of work by the time, with respect to time. And if work is the force times by the distance, okay. So here we come up with the power as a product between force and velocity, okay. So that the rate of work done in this way, we get P equals B square L square V square over R. Okay, so here's the answer for the part of rate of work done. And for the power power loss in the resistor. From the last lessons, we calculate this as the product between the current and the voltage. Or in this case, it is the induced current times the induced EMF. So the current I, so we have the current I as BLV over R. So times by the induced EMF BLV. So hence you get the power of B square L square V square over R. Okay. Here, so you can conclude that the rate of work done is equal to the power loss in the resistor. And we should conclude your example 8. Okay. And then for the last example, in this example, it is special because we get the electric field E to involve in the calculation. So in the part A, the question asks you to determine the direction of the induced electric field. Okay, and what you are given is you are given the increasing magnetic field. So when you got the increasing magnetic field, yeah, so dB by dt. And this is the direction of the magnetic field. Okay, so using the right-hand rule, you should get the clockwise direction. But for the induced EMF, yeah, you should get you should get the clockwise direction for the change of the magnetic field. But for the induced EMF, you should get counterclockwise, as well as the induced electric field, counterclockwise. Okay? So here you can draw some arrows to your electric field. And for part B is to show that the induced electric field is given by this expression. Okay. So we start with the definition of the EMF. So EMF can be written in terms of electric field by loop integral of electric field times the displacement. So from Faraday's law, we can write down another form of Faraday's law as the integrate EDL equals minus d phi by dt. Okay, so in case of the small r, in case of the distance, okay, in case of the electric field outside the region, yeah, outside the circle region. So this is the case of outside r larger than the radius. Okay. The left-hand side of the equation will become just E times 2 pi r. And equals to minus d by dt. And the magnetic field here, the magnetic flux here it is going to be pi r squared. So we use the big R or the radius here because the loop here, the loop of the EMF, it is surrounding the whole region, okay? Because EMF surrounding the whole region. Okay, and times by the magnetic field. But since pi r squared here is a constant, yeah. So what we get for the electric field is will become, so we cancel the pi. So we get r squared over 2r times by the dB by dt, and it is in the counterclockwise direction for r larger than the radius or outside. And then in the case that for for inside the region, yeah. So suppose that this is a circular region of radius big R, and at a position small r, we build a loop of the EMF as yeah. So from Ampere's law again, sorry, Faraday's law again, we come up with E times 2 pi r, and then equals to d by dt, and then in the flux part here, it will be pi r squared b. So it will be just the position because the EMF is surrounding not the whole region, okay? So it's surrounding just only the region with radius r. So we're not using the big R, but we use small r over here, okay? So it's the difference between the two, between the inside and the outside. So for the inside, with r smaller than the radius, so we cancel the pi, we cancel the r. So finally get E equals minus 1 over 2 times the r, and then dB by dt. And it is also the electric field in the counterclockwise direction.